Welcome back. We are on the second part of lesson 3. We are discussing continuity and discontinuity in functions. And this time we're taking a look at an example of a rational function that involves absolute values in it. So kx equals absolute value of x minus 3 over x minus 3. And we have to discuss the continuity of it. Now, first of all, when we deal with absolute value functions, we have to remove the absolute value from the function. The way we do this is by analyzing the sign of the expression inside the absolute value. So we're going to say that if x minus 3, which is the expression inside the absolute value, so if this is positive, it means that we are taking the absolute value of a positive number. Okay? The absolute value of a positive number is the number itself. So the absolute value of x minus 3 would equal exactly x minus 3. So that will make the function kx into fraction line in here. So we know that x minus 3 in absolute value would equal x minus 3 divided by x minus 3. Or in other words, we're going to say that kx would equal 1. Now, we mentioned that x minus 3 has to be positive, right, for this equation to happen. Imagine again, absolute value of a positive is that positive number, all right? So when is x minus 3 positive, though? X minus 3 is positive for x bigger than 3. So the next case scenario would be if x minus 3 is a negative number. So if x minus 3 is negative, that means that we are taking the absolute value of some negative number in here. So whenever we take the absolute value, say for example, I'm making this up, of negative 2, the answer will be positive 2, right? So the answer is positive 2, or I can look at it as the opposite of negative 2, the opposite of what I have in here. So similar to this, we're going to say that the absolute value of x minus 3, if this happened to be a negative number, would be equal to the opposite of x minus 3. So that will make the function k of x into negative x minus 3. That's what the numerator becomes with no absolute value. Again, providing that x minus 3 is a negative number, okay? And that will simplify to negative 1, so kx equals negative 1. Now, for what values of x can this happen? Well, we said that x minus 3 has to be less than 0, which makes x less than positive 3. If we were to draw the graph of this function, then we would say the following. Number 1, at x equals 3, the function will be undefined. Number 2, for x values bigger than 3, so bigger than 3, the y values stay constant and equal to 1. So pretend that this is 1 here. So I'll make this perfect. Here we go. This is the graph. It continues to infinity in this direction. We have to make a point in here that we must have a hole at x equals 3. The function is undefined. Now, for x values less than 3, so to the left of 3, we are going to say that the function equals negative 1, so it will stay constant and equal to negative 1. So if this is negative 1, we're going to say that the function will be going in this direction. Okay? Now we have to also emphasize one more time that exactly at 3, the function will have a hole. This would be the graph of kx equals absolute value of x minus 3 over x minus 3. So if you were to find the limit of the function at 3, it seems that there is a discontinuity at 3, and the type of discontinuity we observe here is a jump discontinuity. And if we were to find the value of the limit, we're going to say the limit as x approaches 3 from the right would equal positive 1. And the limit as x approaches 3 from the left, so in this way, so it would equal negative 1. Now I brought in another example, example 6. We are given the graph of some piecewise functions made of various pieces in here, right? And we have to find and analyze the discontinuity at each indicated point. Starting with x equals negative 3, you see that you approach the function from the left or from the right, the function will approach the value of 1. And the value of the function at negative 3 is also 1. So let's put this into writing. So I'm going to say f of negative 3 equals 1. The limit as x approaches negative 3 from the right side of it, so approaching negative 3 from the right, the value of y is approaching 1. So the limit as x approaches negative 3 from the left is also 1. So left and right hand limits are equal. So that makes the limit equal to 1. The value of the function is 1. And f of negative 3 equals the limit as x approaches negative 3. That means that the function is continuous at negative 3. Moving on at negative 2. Let's define the territories here. So at x equals negative 2, so here is negative 2. The value of the function at negative 2 is undefined. So f of negative 2 doesn't exist. The limit as we approach negative 2 from the left, here we go, we approach negative 2 from the left, the values of y approach 2. Negative 2 from the right, the values of y approach 2 again. So equals the limit as x approaches negative 2 from the right, which means that the limit exists and it equals 2. However, because f of negative 2 is different than the limit as x approaches negative 2, and we're going to say that the function is discontinuous. What type of discontinuity do we see here? So this would be what we call the removable discontinuity. Next example, we have x equals negative 1. So f of negative 1 is negative 1. Oops. Now, if you approach negative 1 from the left and the right, you notice that left limit will be 2. Right hand limit will be 1. So limit as x approaches negative 1 from the left is 2. When you approach negative 1 from the right, then we get positive 1, right? So negative 1 from the right, the graph is here, so that's positive 1. So therefore, we're going to say the function is not continuous because limit doesn't exist. So when limit doesn't exist, that means we have a jump discontinuity. And f of -1 is different than the limit as x approaches -1. Now, just to specify here, at -3 continues at -2, we had removable discontinuity. And at x equals -1 now, we had a jump discontinuity. Next example, again, feel free to pause the video and try to do this on your own. Okay, and at x equals 1, here is x equals 1, we have f of 1 equals 1. So f of 1 equals 1. Now the limit, as we approach 1 from the left, so here we go, approach 1 from the left, the limit will be 2. Approach 1 from the right, the graph is all the way up here, limit is 3. So limit doesn't exist. The value of the function is 1, so we're going to say is discontinuous. The type of discontinuity when limit doesn't exist is jump. Now the last point is at x equals 3. So at x equals 3, f of 3 will be 1. So at x equals 3, the value of the function is 1. Now, the limit as we approach 3 from the right and 3 from the left. Okay, let's take a look. So 3 from the left, the limit is 1. 3 from the right, the limit is infinity. So whenever we see infinity for one of the limits, we have a non-existent limit. I mean, one side is 1, the other infinity. So the sides don't agree. Limit doesn't exist. And whenever we see infinity in a limit, we have an infinite discontinuity. So, oopsie, discontinuous, obviously. And the type of discontinuity is infinite. Okay, so this was lesson 3 of unit 1, calculus, and we discussed continuity and discontinuity of a function. You have more practice questions you can work on, and I hope you found the lesson useful, easy to understand, and I thank you for listening. Bye for now.